Welcome to a complete course in General Relativity. This series of videos will guide you through the fundamentals of general relativity, starting from the basics and building up to more advanced concepts. Whether you are new to the subject or refreshing your knowledge, this course will provide you a step-by-step approach to mastering general relativity. In the first video, we would look into what is called the nature of space and time. Well, the notions of space and time that have dominated the physics until the beginning of the 20th century are strongly bound to the thoughts of this person, Isaac Newton. However, in the 17th century, two philosophical currents confronted about the nature of space and time. While Newton defended the idea of absolute space and time, whose existence does not depend on physical phenomena, the relationists thought that space and time are not things in themselves, but emerge relations among material objects. Well, in the philosophy of space and time, relationists are those who believe that space and time do not exist as independent entities, but only as a network of relations between objects and events. As you can see right on the screen, that relationists define space and times that do not exist as independent entities, but something like this: only as a network of relation between objects and events. So they believe that the existence does not depend on physical phenomena, which was Newton's idea, and this new thought believes that space and time are not things in themselves, but emerge from relationships among material objects, that is, the objects and the events. In themselves, they emerge among material objects. Now, the main exponent of this idea was the German philosopher, polymath, mathematician, and a great person, Gottfried Wilhelm Leibniz. In his correspondence with Samuel Clerk, who was a friend and a disciple of Isaac Newton, Leibniz stated this: "Space is that order which renders bodies capable of being situated and by which they have a situation among themselves when they exist together, as time is that order with respect to their successive position. But if there were no creatures, space and time would only be in the ideas of God." Now, this seems to be a little bit crude, I would say, a statement in terms of Leibniz's letter to Samuel Clerk, but it gives profound insights in our understanding of space and time. First is that space as order of relations. So Leibniz defines space as an abstract order that allows bodies to be situated relative to one another. Second is time as sequential order. Similar, time is the order of events in succession, not an independent entity. It is the structure that organizes the sequence of events. Third, space and time depend on objects. According to Leibniz, space and time exist only as a relation between actual objects or events. Next comes, Leibniz adds that in the absence of creatures, space and time exist only as ideas in God's mind. Well, this implies a kind of a theological dimension where space and time are contingent upon God's understanding or conceptualization. Finally, he says that there is no space outside the material universe. Space is bounded by the existence of material objects, rejecting the notion of an infinite absolute space which is independent of matter. Now, going ahead from this, what we can see that the Newtonian notion of absolute space was found unacceptable by Leibniz. Why? Because these two universes, whose bodies occupied different absolute positions but identical relative positions, would be indiscernible. This word carries profound influence, would be indiscernible. What do we mean by that? Let us look a little bit more into this statement of Leibniz. The first is that Leibniz's principle of the indiscernibility of identical states that two things cannot be different if they have all the same properties. Second, he says, if all bodies in two universes occupy identical relative positions, no observation could distinguish them based on absolute space. And third, he says that since the two universes would be identical in every observable way, Leibniz argued that the concept of absolute space is redundant and unnecessary, as it adds nothing to the physical description of the universe. Now, the Newtonian notion of absolute space was found unacceptable, as we have seen. But for his part, Newton considered that the space has its own reality, independent of the bodies residing in it. So even, as you can see on the screen, that the empty space would be conceivable. In Newton's physics, space and time are the seat of the physical phenomena. But remember, the phenomena produce no effects on them, as the space always remains equal to itself and the time passes uniformly. And in his famous work, which is celebrated, Philosophiae Naturalis Principia Mathematica, he makes a remarkable statement. Newton says this: absolute true and mathematical time of itself and from its own nature flows equably without regard to anything external, and by another name is called duration. Relative, apparent and common time is some sensible and external measure of duration by means of motion, which is commonly used instead of what is called a true time. Now, this statement again requires a little bit of our attention. Now, from this particular statement, you can pause and have a look onto this statement. The first thing which emerges is the concept of absolute time, because Newton defines absolute true and mathematical time as an independent entity that flows uniformly, unaffected by external factors. There's something which is called a relative time. Relative and apparent and common time is how time is measured through observable processes like the movement of the sun or clocks. So from here, what we can find is this: absolute time is a theoretical and unchanging, while relative time is practical and depends on the way we perceive or measure it through the motion and physical phenomena. So from here, what we can summarize is that Newton contrasts the ideal concept of absolute time with the observable imperfect way we measure what we call in daily life. The controversy between relationists and absolutists subsided in the century following Newton's scientific triumphs. However, it remained dormant only to re-emerge and resurface in the late 19th century. From this concept of space and time, we come next to our video as we go into what is called the geometric properties of the space, coming up into the next part of our video. As we see that the only space geometry known at the time of Newton was only Euclid's geometry. Although it is little known about Euclid's life, not even there is certainty that he really existed, it is believed that he taught in Alexandria around 300 BC, and Euclidean geometry is the same geometry that is nowadays studied at school. It is just a logical system from a set of definitions, postulates and axioms. However, their axioms and postulates are completely intuitive and natural. Only the known one, which is called the fifth postulate, whose content is equivalent to something which you can read on the screen, to state that one and only one parallel line passes through any point outer to a given straight line. Now, it seemed to be a little natural for many mathematicians who wondered whether it would be possible to create I would say, a new geometry. Will it be a little natural for mathematicians who wondered whether it is possible to build an entirely different geometry by replacing Euclid's fifth postulate? Well, out of that, the prince of mathematics, his name was Carl Friedrich Gauss, intrigued by the question, decided to make an experiment to find out whether or not the fifth postulate was true. Now, in order to do that, Gauss made an experiment going to the mountains. So Gauss decided to measure the angles of the triangle formed by the tops of the mountains in Germany. And he selected the Mount Brocken, Mount Hohenhagen and Mount Enselberg, all of them forming this and this line, which you can understand is a triangle. Now, the choice of the mountains, these are made in order to form a triangle. So the purpose is that he wanted to test whether the sum of the angles of this triangle, large triangle I would say, would equal 180 degrees as predicted by Euclidean geometry. And if there is a deviation, remember, it would indicate the curvature of space, implying that Euclidean geometry might not hold on a large scale. So Gauss planned to measure the angles of the vertex of the triangle using geodetic techniques, which are not going into this. But however, the main thing that he found is the sum of the experimental determinations of the angles showed a very good agreement with the results predicted by Euclidean geometry. Although Gauss never published the results, possibly due to the difficulty of measuring such tiny differences over long distances, this was what he found. So in conclusion, we can say that Gauss's experiment did not provide conclusive evidence at the time. It was a significant early attempt to empirically test the nature of the geometry of space. And what he found, that more or less the space, we can say, is approximately Euclidean. Now, accepting that the geometric properties of the space are those of Euclidean geometry, we can build what is called this one, the Cartesian coordinate systems, to locate a point with respect to a reference. Now, here is a kind of a diagram. So you can see that the Cartesian coordinates of a point P, this one, are obtained by measuring the distances between P and each one of the planes. This procedure implies to draw P, the sole perpendicular line to each plane, as you can see right on the screen. Now, we can calibrate these axes to measure the Cartesian coordinates directly on them, and the coordinate origin being the point O, where the axes actually intersect. Now, if the Cartesian coordinates between P and Q, as given in this figure, if you can have a close look of this, the Cartesian coordinates of 2 points, this one, P and Q, in a given reference system, then the distance which we call d sub PQ, can be computed using Pythagoras' theorem. Right on the screen, you can see the simplest form of the Pythagorean rule, dpq square equals to this one plus the second plus the third, whole squared. So if the points P and Q now move with respect to the reference body, then their Cartesian coordinate changes with time. So in that case, what will happen? The calculation of the distance requires a simultaneous determination of the coordinates of P and Q, and the result is a function of time. So physics before Einstein, I mean to say the physics that we are talking right now, regarded distance as this invariant quantity. That means independent of the reference system. Distance was considered, if you take as a property of the pair of absolute positions, this one P and Q, at the time when dpq is evaluated, we can take that this assumption will play a fundamental role in the coordinates transformation, which we will look up later in this series of videos. So from here, what we can find out is that it is thought to be a property of their absolute position at a given moment in time. Few things emerges out of this. The first one is that distance is evaluated at a specific point in time, assuming space is static and unchanging. The second we find is that distance is not relative. That means is an inherent property of the absolute spatial positions. And the third, this reflects Newton's idea of absolute space, where positions exist independently and distances are fixed by these positions. Now, with this geometric properties of the space and time, we now, from Newton, we move a little bit back, not a little bit, quite a old time, and what we see is this one, Galileo and the laws of motion. During the centuries of Aristotelian tradition that preceded the famous Italian mathematician astronomer Galileo Galilei, the motion of a body was associated with the action of a force on the body. Again, I repeat, the motion of a body was associated with the action of a force on the body. If I take the quotation of Aristotle himself, he wrote that the moving body stops when the pushing force gives up acting. Now, in order to demonstrate this, let us imagine this ship or a boat which is sailing, and let us imagine this to be a stone, and that drops from the top of the mast of a sailing boat. It drops and drops and drops and drops over here. Now, according to the Aristotelian thinking, the stone of the mast of a sailing will not fall at the foot of the mast. Why? The reason is that when it leaves the mast, the force needed to conserve its state of the motion, that means communicated by the boat, is going to disappear. Therefore, what will happen is that the stone will not follow the advance of the boat, will follow backwards, that is around this, and this. So the stone will fall backwards of the mast. Now, if I take the same diagram, we can see that Galileo actually defied the Aristotelian thinking by asserting that the stone does conserve the state of motion it had before dropping, so it will follow the boat and fall in the foot of the mast. And this is the animation. It drops and drops and drops and drops over here. So here is that it will follow the boat and fall at the foot of the mast. Now, inspired by this was the famous Galileo's experiment. He proposed that if you dropped two objects, although there historically this falling of the cannonballs has got a little bit of controversy, but we are not going into that. If you drop two objects of different masses from the same height, they would hit the ground at the same time. If air resistance was negligible, this contracted the earlier Aristotelian view of the heavier objects that falls faster. Now, to verify Galileo's claim, Pierre Gassendi dropped objects of different masses from the top of the Hôtel de Ville in Marseille, and he carefully observed their fall. And so the result was that Gassendi's experiment showed that the objects did indeed fall at nearly the same rate, confirming Galileo's hypothesis. So Galileo's hypothesis that in a vacuum or without any air resistance, all bodies fall with the same acceleration due to gravity regardless of their mass. So from here, what we can see, few important points. Number one was that Galileo defied Aristotelian thinking, claiming that a stone dropping from a moving ship would conserve its initial motion and laid at the foot of the mass, not behind it. The second was that Galileo presented this idea as a thought experiment, though the actual experiment was performed by Pierre Gassendi in 1641. By rolling small balls on the tables, as you can see here, Galileo examined how motion persists. He observes that while balls stopped due to friction and air resistance, in ideal conditions, no friction, they would continue and continue and continue to move indefinitely. So from here, what we can get is this. Galileo concluded that objects remain in motion unless and upon by external forces, laying the foundation of the concept of what is called an inertia. This is a famous book by Galileo Galilei, later translated by many authors, Dialogues Concerning Two New Sciences. And you can pause the video and you can read this statement, which marks a historical importance both in mathematics and physics. I'm not going to read the sentence line by line, but what I'm going to tell a few foundational blocks. First is that inertia, the concept of inertia emerged and is the tendency of an object to maintain its state of motion or rest unless acted upon by external force. So Galileo's statement directly supports this. The second is what is called perpetual motion. Galileo's thought experiment suggests that in ideal condition, absence of external force, motion is perpetual. And third is that it absolutely challenged Aristotelian view, which claimed that objects naturally comes to rest unless continuously pushed. Instead, Galileo told that motion does not naturally cease unless there is no external force to cause deceleration. So you can say from this statement that it is a kind of a precursor to Newton's first law of motion. I mean to say something emerges out of that. Now, in the thought experiment that we saw of the stone and the boat, Galileo reveals that the persistence of motion implies that the experiment has the same result, either the boat is moved or sailing. This is very important. The experiment has the same result, either the boat is moved or sailing. And hence from here what we get is that in both cases the stone falls at the foot of the mast. So from here what we can find is that Galileo broke the idea that the motion needs a force. On the state of motion is, on the other hand, he showed that it is not possible. So if you imagine yourself riding inside the boat or inside a moving vehicle, he showed that it is not possible to detect the motion of the boat. That means it is undetectable by means of an experiment made in its interior. What does that mean? That the laws of physics on the boat sailing do not differ from the laws of the moved boat. And this is something you can verify very well in conclusion into your daily means of transport. So the velocity of this bus, as you can see on the screen, is not detectable in its interior. That means by watching through the window, we just detect that the vehicle has a motion relative to the earth. Instead, we do observe that the variations, for example, the turns, either in direct or magnitude, when the bus takes a curve or jumps at the union of two stretches of railroad, when it brakes or it accelerates. So we will take a pause of today's video where we understood Galileo and the laws of motion. However, this is just the first video in our series of videos of learning Einstein's general theory of relativity, building up right from the basic foundation up to its very advanced concepts. So I would like to immensely thank you for watching this video. If you have liked this video, please hit on the subscribe button of my channel Physics for Students and click on the bell icon to get all the notification from this channel. You can contact me at this email ID, and you can like and subscribe to my other channel, General Relativity Explained. Further, you can follow me on my Facebook, LinkedIn, Instagram and Twitter account. Physics for Students will continue with this series, and I will see you soon. But till then, goodbye.